So next up on the menu, we have axis realigned bounding boxes, or basically axis aligned bounding boxes which have been recalculated from a previously uh, determined axis aligned bounding box with a rotation. So, or other transformation, by the way. This can also apply to scaling, but not to translation. So as we talked about in the last lecture, what if you have this situation where you have these two axis aligned bounding boxes, but one object has been rotated, and obviously when they collide, this is not representative of the true calculation that we're doing anymore, because the left or the green bounding box, we're calculating actually an axis aligned bounding box, the rotation gets lost in the mix. So while this may result in a calculation, it's not correct. So how do we deal with that? So what we need to do is we need to take this green box and get the axes back into the correct oriented reference frame. So how do we do this? So if we take a look at this example from the code, here's a axis aligned bounding boxes that's surrounding the creeper model, and you can see on the bottom there are these axes kind of drawn in to represent the axes of the model versus the axes of the system, which are the blue and the red and the green. And in our case with the model, you can't see the green, but the blue and the red. Now, if we look at it orthographically, we can kind of see the blue coming out at us and the red coming to the right. Now, when we rotate it, however, you can sort of see that no longer are these, some of the axes are still aligned correctly, but clearly the y is incorrect and the x is incorrect as well. As you can see here, so yeah. So what would we do? Well, what we need to do is we have the white axis aligned bounding box, but what we need to do is determine what is the new bounding box that is resulting from this transformation. And you can kind of see here, right, it sort of is a diagonal. So before we had a very rectangular box, and now we're going to have a much more square box, because that right top point is a little bit different than it used to be. And you have to keep in mind here, one of the more kind of common mistakes that are made when you're realigning a bounding box is you have the half vector and you say, okay, well, I have my max point and my min point, I'm going to rotate them, now I've got a new box. That's not really true, right? Because while your maximum x point here is still the same maximum x, right, the top right corner of the creeper's head, the maximum y is no longer the same point, right? The maximum y is actually the left point on the top of the head. And so this actually kind of demonstrates a little bit of what you have to do to figure out which point is the maximum. Now you have to actually go through your bounding box as it exists and determine the maximum displacement of each one and recalculate that bounding box based on that. As you can see here, now our maximum x is still the maximum x being the top right corner. Our maximum y is actually no longer the top right corner. It's still the same y, but it's a different y, like the 2 points on the top of the head are in different y positions. So you have to choose the one with the highest y that you have. And yeah, this is what's nice about this. And what's cool about this is you don't actually have to check the model, you just have to look at the bounding box of the model. And that's nice, because if you have a really complicated model, right, calculating the maximum x and y of an oriented thing, you could be checking millions of vertices. So in this case, you're just checking not even vertices, you're just checking the a rotated half vector and saying, okay, max, 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 you know, and it's like maybe 8 checks and recalculations. So you do have to do this every single time, unfortunately, that you rotate, but it's can be pretty quick. So yeah, as you can see from the top and from the right, or from different views, we can see that the bounding volume has rotated, but now our yellow box is oriented to our bounding, to our world view frame of reference. There are no funky things going on. So even though the underlying model, the underlying bounding box, the axis line bounding box, the original, has its own frame of reference, our new yellow bounding box, the axis realigned bounding box, is correct. And you can use that to do calculations of collision with other axis aligned bounding boxes. As you can see here, the points now are defining the kind of bounds of this box, and these points, again, as I was mentioning, are relative to the half vector of the original box, not to the vertices of the model, but you can see that they perfectly define the size of that box. And so it doesn't actually matter what rotation you do. You can have an arbitrary rotation, you can do whatever you want. The underlying box will sort of squish and grow and change shapes and do funky things based on whatever transformation you apply to the underlying geometry. And that's really nice, because now we can use that bounding box to determine what it is that we're doing. And by the way, I want to add this image, and a lot of times when people describe bounding box and bounding volume hierarchies and all this stuff, it's very like confusing, because you're like, wait, do I have to do this every time I rotate? Do I have to always update these values? Like, it seems like a lot of work, and you're right, that's not what you do. You calculate these each time. So like when we demonstrate these videos, we debug it, we're calculating these every single frame, because we as human beings want to see that it looks right. But in an engine, you're not doing this every frame. Sometimes you're not even doing it for seconds or minutes. You're only doing it when you think a collision may occur. So again, going back to the last lecture I was talking about, where you want to exit out early. So imagine you have a collision detection engine. The first check you do is not even a bounding not even a bounding sphere. You just take the measurement of the, like, how close are they? Are they in the same part of the world? Are they even in our scene? You know, you don't want to check collisions for things that aren't loaded, blah, blah, blah. So it's like your first level of, like, is it even there? Does it even exist? Then you do you have the half vector, right? That's the one thing you do. You calculate that one time, and you never calculate it again, right? And so you have your half vector, and you use that to determine, well, the radius of a bounding sphere is the magnitude of a half vector. So, okay, you can check the half vector using a bounding sphere, and then check all different things. Cool. Now we know, okay, these objects there's no way they're touching, so we don't even do this. Then the next one we do is we do we want to do a bounding box check, an axis aligned bounding box check, but we know that there's a rotation. So if there's no rotation, you do the normal one. If you know that there's a rotation, then you calculate these points. You calculate that new oriented bounding box, that new axis aligned bounding box. And that's when you do this. So the idea here is that you're only going to do this calculation once in a blue moon, by comparison to a sphere or to utilization of some kind of hierarchy or a data structure that we'll talk about later in the class too. But you can kind of see that while this looks like a lot of work, it's not actually being done that often. It's only being done to figure out if, you know, at a certain point of confidence. So to get the axis realigned bounding box, as we talked about, we need to figure out what the 8 corners of the bounding box is. So we take everything and put it into world space. Keep in mind, everything's in world space. Now we have the kind of half vector, and we can apply to the center point the half vector in all its different permutations, right? And we want to do now the min and max of each one of those corners, just like we did for the axis aligned bounding box. And then we figure out the width and the height and all that stuff. And that's it. That's really it. Like we take the original information of an axis aligned bounding box, we orient it, now we do it again on that bounding box, and because we're already, you know, getting the min and a max and everything, we don't actually have to divide everything by 2 to get the half vector. We just use those values verbatim. So you can kind of see here the example of 2 objects oriented with a respective bounding box to them. Right now, this demonstrates an overlapping of the axis-aligned, like the axis realigned bounding box. You can kind of see the limitations of an axis-aligned bounding box. In a way, you're almost just as good off in using a sphere for this particular test, because the sphere would also overlap and also have a similar amount of error. An axis realigned bounding box will have less error than a sphere, but worst case has about the same, right? So like, this is sort of the trade-off. Ultimately, you can have these very incorrect collisions with axis realigned bounding boxes. However, they're still very useful, and we should all know how to do them. So similarly, as we were talking about, if you do actually apply a sphere in this case, you wouldn't actually have had a collision. So in this case, actually, the oriented bounding box, the realigned bounding box, has a worse error, but still not something too much different. But you can kind of imagine, as I was talking about before, if you had a pre-test using a bounding sphere, so then you would not even get to the bounding box test, and we would know. So you can kind of mix and match. In this case, right, this would represent a collision while still technically not colliding. It's a lot closer than before. So it's tough. You'll actually find spheres and oriented realigned bounding boxes checks being used for like first-person controllers in video games. So if I'm like walking up to a wall, or if I'm walking up to another character, I don't actually want to collide. I want to be kind of far away. I want a certain distance. I want a certain buffer. And so this tends to be something that is not as used. It is used in those kinds of scenarios, and not necessarily for like objects falling onto each other, unless those objects are billiard balls or of a particular geometry. So yeah, that's about it for this subject. Next, I'm going to talk a little bit about the separation axis theorem, which then allows you to take the next step and to actually represent these objects with oriented bounding boxes, which would allow us to have those red boxes here actually checking against those versus checking something larger.